Hello everyone, welcome to our Open Security Summit 2020. We are very happy to host you here and hope you are also happy to be here with us. What to expect from our summit? It is we really expect that you will be participating actively. We will care about each other, mutual respect, of course, and we challenge each other, and we just try to find solutions and try to keep to learn from each other as much as possible, because these are all training sessions. So the main goal is really learning. So what we respect in our summit is openness, and everything in the summit will be recorded, will be live broadcasted, and if you really want to be anonymous or you want to be just not share your name or something, please take personal precautions, and then otherwise everything will be shared in our summit websites or in YouTube. So just respect is the key for us. We collaborate with each other. We try to find solutions together, no discrimination, and everything really open. And, if you have questions, please come up with your questions, ask during the session, or write in the chat so that we can then answer. Thank you very much, and I'm giving the floor to our speakers. I will just stop my slide sharing, and we can continue from there.
Thank you, Tatvik. Hi, this is Paul Burke from Glasswall Solutions, and I've also got a guest here who's going to participate in this session with me, Dr. Tim Lunn from PA Consulting.
Hi there.
And this session was really set up to highlight a document that the UK National Cybersecurity Centre have published on how to safely import documents into an organisation. That's called the Pattern for Safe File Import. Now, it is quite a stringent pattern, as you can imagine, for use in the intelligence community space, but it is also applicable to commercial. And the objective for this session was trying to get a discussion going about making people aware of this safe file import pattern, what it means, and how you can implement it, and an example of how Glasswall has partnered with PA in creating something that is matching that pattern defined by the NCSC. So maybe at this point it might be useful, Tim, if I ask you to just give an overview from your perspective of how we've implemented against that pattern with the PA Glasswall joint product.
Absolutely. Okay, I'll do that. And yeah, absolutely iterate what you're saying there, Paul, that this design pattern from the NCSC is designed to encapsulate best practice, and it's published so that it can be used more widely than just in government and defense and security. It's absolutely meant for commercial organizations to use to protect themselves. So what I'll do is, let me give you, I've got a couple of slides here that just give an overview of what the pattern says, and then I can talk about how we've worked with Glasswall. Let me just grab this.
Yeah, and I should say to anybody as we're going through this, this is intended to be a discussion. So
yeah,
if you've got any questions, anything you want to challenge as we go through this, just shout it out.
Yeah, absolutely. I mean, I've got half a dozen slides, but they're really, in case somebody asks a question, I can refer to them. So please do interrupt. Can you guys see this? Can you see the screen?
Yep.
Great. Yes. So to give a top level view of the idea of the pattern, it's about trying to make it safe to import data, as Paul says, And the traditional way of doing that for high threat environments is to use a data diode. As the name suggests, a data diode is something that lets data through in one direction. So you can see, I don't know if you can see my mouse, but you've got a data diode and you're bringing your data into your organization. The reason you use a diode is that it stops attackers being able to signal back out to get command and control information, and it stops them exporting the data that you're trying to protect. And traditionally, you'd follow that diode with a process that would check that everything that's come in is safe. And the best way of doing that is doing a transformation, so that you've got a protocol break, and then a verification stage or a check stage here, and then an inverse transformation, and you can use your material on the high side. What NCSC have said is that an even better way to do that is to do the transformation before the data diode, so on the low side, as they see it, on the less trusted network. And then as you bring the data through, you carry out syntactic and semantic verification, and we'll go on to that. And that gives you this improved model. So my next slide, okay, so one point to note is that this really is relating to structured data. And that's what I have been dealing with, and that's what we've been working with Glasswall to look at. So structured data could be things like protocol messages, or much more complex structured things such as PDF documents, Word documents, and that's absolutely where Glasswall's software comes in. The contrast is with unstructured data. So unstructured data where you can't do this transform verify process, what you're basically going to do is you're going to import it and you're going to scan it. That's not what I'm interested in here. Okay. So this is the NCSC safely importing data design pattern. What they say is that the first step is to carry out a transformation of your incoming data. That helps you to break any attacking code using a protocol break, and you transform it into data that is simple to verify. You then send your data through the diode. So they've got a sending and receiving function, and then you carry out the verification, so the syntactic and the semantic verification. So syntax is the structure of the data. If you've got a comma, it must be followed by either a white space, a new line character, or an alpha character. It can't be followed by an exclamation mark. You know, that's the syntactic structure that you're checking. The semantic verification is the meaning of the data. So you're doing a much more complex check there. You are making sure that if this says it's an integer in the range 0 to 10, that you haven't got a field representing the value 3 million. Okay, so this is the NCSC design pattern. What we've got here, I've just drawn a blue box around the thing that our hardware does. We've got a data diode, and it does syntactic verification in hardware. And so we carry out those 2 stages in the import process in the hardware, and then pass it on to the software. Okay. And then this is my final slide, really, before I hand over to you, Paul. So what we were really keen to work with you guys on was to show how your software could be used to carry out those transform and check stages. And we looked at the mapping of your processing onto those NCSC steps in that import process. This is my representation of how we do that. So your software is divided into 2. We do the deep inspection first. It outputs data in a language that we call sizzle, and then that sizzle is verified up on the high side in software. Okay, that's me as my overview. I can obviously answer more questions later, but over to you, Paul.
Thank you. Has everybody got any questions before we jump into the next bit? Everything clear so far? Okay. All right. Yeah, let me just see if I can.
I should stop sharing, shouldn't I, so that you can?
Yeah, thanks. Okay. So I took the liberty of, I'm using one of Glasswall's tools here called the Forensic File Workbench, and it's just to kind of by way of expose you to how we take what Tim describes, you know, as the Office documents, for example, or PDFs. Very complex document, very difficult to kind of do that with kind of semantic and contextual checking on it.
Yeah.
So what we do is our engine is used to going through those files, and inside the files are made up of structures, and each structure has a very clear definition of what it's made up with what bits and bytes are in each one, what values are allowed, what relationships each one of those has. So what we do is we read the entire file and all of its structural elements into a tree structure, and then we output that in the sizzle format, which is basically a markup language that says, here is all the definition of all the components. So it brings a complex, if you like, binary structured document down to something that can be checked and validated with markup. Now, when you do that, there are also, you know, blobs of data within there that may represent your binary. So there are some valid pieces, such as embedded images, that you may want to deal with differently. This is just an example of a set of markup. This is for, I think, just a JPEG file, which just defines each of the content items within the JPEG. So this is all then easily kind of syntactically and semantically checkable at that point. So what we are doing is, in that kind of transform phase, is turning those complex binary documents into this kind of language that then ends up being checkable by the gateway. And there are some kind of interesting spin-offs of that as well, where we can easily extract elements that may be other embedded objects, such as images, and we can do secondary checking on those. So one example might be, we take an image file out, and that might be a JPEG, and we know some customers, the only way they'll verify images is we convert them to a bitmap, we make sure that it's readable and complies with a bitmap format, we reconvert them back to JPEG, and we reinsert them in when we do that reconstitution of the document. So this is what it's all based on, the fact that we can turn any complex document structure into this sizzle markup language. But we also do this into raw XML as well, which is what this example shows. So the markup language, we can comply with different languages, but the content within the document remains the same. So just an example of that detail that we are kind of expecting. Does that make sense? Questions about that? Okay. So the other thing, just so we're clear, is what we are doing within our engine, as I say, is whilst we can read that entire structure, you know, the essence of what the Glasswall engine does is two things really, is what we call sanitize and remediate the document. So remediation is finding anomalies in the structure that doesn't comply with the standard. And you heard Dennis earlier in other sessions talk about ISGs, which talk about the standard definition for the files. And we find and fix those anomalies. And then the other thing we do is sanitization, which is on deconstructing the file like this, or on reconstructing it, we can target and remove certain types of active content that may be high risk. So if you didn't want your image files to appear, or you didn't want links within documents, we can target and remove those objects. So when we reconstitute the file, those things are no longer there. So that's the essence of what we're doing behind the scenes. We expose all that document detail. It then gets all its checking done on the gateway, and then we're reconstituting it and applying the policy on how we reconstitute the file. And when we do that, any file analysis that we go through will basically look at this, and it says, it defines what kind of file it's found, the size of it, what kind of threats we found in the file, and this is that active content, and then actions we've taken on the file. And in this case, this is a clean file, so there was no action to take. But if there is, then you'll get a long list of the particular actions that we took on the file. That's pushed out as kind of report data in a markup format that can be consumed and acted on. So that's what's going on behind the scenes, and this all works end to end, and it's compliant with that approach that Tim described that the NCSC are defining in their safe file import pattern. Does that make sense to anybody? Anybody got any questions or? Oh, got a thumbs up from Onkiran. Makes sense. Good.
Yeah. I guess for each structured document that you need in this process, you would have to define this out, right? And
you'd have to define the what, sorry?
You'd have to define all the sanitization rules and all of it out for every structured.
Correct. Yeah. So but that's not a huge amount of data. The remediation works automatically. And if I just click on here, this is the set of sanitization, what we call content flags that need to be set. So it's not as if there's thousands of these things. There's only 10 or 20 per file type as to what kind of things to target. So it's a very manageable set of things to control. And because the file types have a pretty stable structure to them, the structural definition of the file changes quite rarely. These don't need revisiting an awful lot of times. Once you've got a policy that suits you, then there's not a lot of maintenance involved to stay on top of that. Does that kind of address your question or concern?
Yes.
Yeah. So it's fairly easily manageable.
I was going to just add something onto that, Paul.
Yeah. Go ahead.
That one of the advantages of the approach where we're combining the hardware and software is that while the hardware is very difficult to modify, and the software is easier to modify. So the way we've partitioned it is such that the information going through the hardware, going through the diode and going through that syntactic check, that does not need to change with the change in file type. So the sizzle that Paul mentioned, which is going through the diode, is application independent. And that means that we can create the hardware, we can do lots of testing and inspection on the implementation, we can get it accredited, and then it doesn't change. And then the software that is wrapped around it is what makes it application specific, and so that's particularly flexible.
Good point.
From the NCSC perspective, though, the diode does not need to be hardware, right?
It doesn't, but I think my experience, diodes are almost all kind of hardware-based devices. I haven't seen a software-only diode that's used in a great, any breadth.
It depends on the application.
Yeah.
You're right. The NCSC is quite right in that it does not specify that it must be hardware, which is actually an interesting contrast to NSA, where they now specify that it must be hardware for particular applications. but you know, the hardware device gives you that assurance that you've got that guaranteed one-way flow. So it's a straightforward thing to assess and check that it is working. Whereas a software diode is obviously can be more cost effective, but it is not as secure in general.
Cool. Yeah. Any other questions on Kieran?
No, thank you.
Do you see, are you considering something like this in use in your organization?
Well, I'm trying to absorb as much as I can from all these patterns, and while I've not, I mean, we do ingest files, and I've been looking at putting some security into that ingestion process.
Yes.
I'm not sure, my organization would probably be looking for something at this level of security, but these concepts can still apply even without necessarily having a hardware diode. There are certain things that you've discussed and you've pointed out. Conceptually, they can still apply in various ways to the processes that we're doing. So my intent here is actually just to absorb. It's about building some kind of knowledge of what are the processes out there and what do people do. And I'm just trying to then map it to what can we do on our side.
Yeah, gotcha. Yeah. And I suppose to me, there's a couple of perspectives to that. Is the technical complexity of putting something in place, but also the cost. And I feel like where we've got with this combined solution, the cost is on a par with some of those more traditional commercial solutions.
Yeah.
And the technical complexity, frankly, is pretty similar too, from my kind of perspective. But Tim, I don't know whether you've got any other comments you want to add on that.
No, that absolutely. That's one of the drivers for the work, is to show that this can be done cost effectively, and that therefore it's not a highly specialized, complex product appropriate for use by just the military. This is now within the reach of commercial organizations, and so while government organizations are mandated that they must use certain defenses, and there are standards documents that define the requirements, in the commercial space, it is obviously a cost-benefit analysis, and they need to justify their investment in terms of the reduction in the risk to their operations. And so critical in that is reducing the cost of deploying these extremely secure solutions. Because if you can eliminate that risk or reduce it to very, very low levels, you can certainly justify the kind of expense that it is now possible to bring the cost down to. And commercial organizations connecting to the internet all tend to obviously have these kind of security problems. They cannot exist in isolation. They've got to interact with their customers. They've got to bring in documentation, orders. There's a continuous flow across the organizational boundary. And so these kind of security measures, where you are guaranteeing that something that you bring into your organization is safe, is going to greatly reduce the risk of cyber attack. And making that affordable to commercial organizations is a new thing.
Yeah, absolutely. Okay, so I guess we've covered the essence of what's the patent do, how have we instantiated it in the combined PA glass wool product. I don't know, Dennis, are you online?
I think Dennis was in another session. He's mentioned from the beginning that he might be. Do you want to stop the recording, or?
Is there any other things you think it's worth us going over from the point of view of what we've done?
No, I don't think so. I mean, I think we've covered. I guess one point I didn't make was, why are we combining the hardware and the software? To go to the expense of a hardware diode is you're using that because you've got a high impact risk that you want to reduce. As I say, the objective of the work we've been doing is to reduce that cost of deploying this kind of technology. But why would you use a hardware diode as opposed to a software? And the idea that we've been working on is that syntactic verification means that you can guarantee that everything that comes out of that hardware diode is safe. The fact that it's in hardware means that it is much more difficult to attack that syntactic checking. It's not running in a CPU that you can crash, that you can then begin to exploit, that you can modify. It's running in programmable hardware where the control plane is separated from the data plane. It is incredibly hard to attack. What that means is that the data coming out of the diode, as I say, is relatively safe. And that means we can reduce the cost of implementation of the software that subsequently follows. So the hardware is protecting the software that follows the diode. And the software is carrying out that more detailed semantic checking, confident that what it's checking is not trying to attack it.
Yeah, and Tim, is it worth talking about the nature of the diode technology that you guys use? Because it feels like there's a couple of broad approaches, and a lot of people have looked at diodes and said they're quite costly devices, particularly when they're based on pure optical technology, whereas you've managed with the PA diode to get certified with a different technology, right?
Yeah, absolutely. So the traditional data diode is an optical device. So you're basically using an optical isolation. You've got an LED or a laser on one side, and you are transmitting that light to a photodiode on the other side. And that means that you've got that sort of one-way flow of photons through your optical fiber or optocoupler. So that's the traditional way of doing that one-wayness. But there are obviously many other ways of doing a one-way information flow. And so one of the things that is implemented in our diode is that it is an electrical unidirectional link. So the technologies used nowadays for communicating around printed circuit boards are actually inherently one way. And typically on a PCB, you would actually connect two lanes connected in opposite directions. You don't have to do that, and that gives you a one-way link. And you can show that that is a one-way device. Instead of photons flowing in one direction, you've now got electrons. You've got a transmitter that is useless as a receiver. You've got a receiver which is not able to transmit. And so you've got exactly the same assurance of a one-way flow, but it's electrical as opposed to optical. And we found that greatly reduced the cost. So we were just connecting together our multiple FPGA devices that we use, using this electrical connection and getting a very secure, guaranteed one-way flow that could not be subverted unless you respan the PCB, which is exactly the same threat as with an optical device.
Cool.
Thank you.
Okay, so I think we've covered everything we wanted to, just to highlight the solution and the NCSC pattern Tatevik. So why don't we hand back to you?
Yes, thank you very much for the session.